All right, let's dive in. Today, we're talking about the technology that's quietly giving AI something it desperately needs: a long-term memory. And believe me, this is a total revolution happening right now in the very architecture of how we handle data.
So, you ever had this happen? You're having this incredible deep chat with an AI, and then you start a new conversation, and poof, it's all gone. The AI has no idea who you are. It's like talking to a genius with total amnesia. Well, today, we're going to look at the amazing tech that's fixing this exact problem. Okay, so here's the plan. First, we'll tackle AI's memory problem. Then, we'll meet the database that thinks. We'll dive into how it solves an impossible problem, look at the good enough answer that makes it all work, and wrap up with the new database war that's heating up. So let's get into it. The big issue here is that large language models, or LLMs, are what we call stateless. Now, what does that mean? Well, they have all this incredible general knowledge from their training, right? But they know absolutely nothing about your stuff, your documents, your company's private data, or even the conversation you had with it 5 minutes ago. For these AIs to be really, truly useful, they have to be connected, grounded in our specific factual data. And here's the thing, the old way of finding that data, it just completely falls apart. Traditional search is all about keywords. You type database, and it finds every document with the literal word database. Simple. But what if you ask about systems for storing information? A keyword search is going to come up empty. It has no idea what you mean. This is where vector search comes in, and it's a total game changer. It doesn't look for words, it looks for meaning. It understands that database and systems for storing information are semantically, conceptually, the same thing. That is the key to giving AI a real memory. So this incredible need for a search that understands meaning has basically created a whole new kind of technology, the vector database. And let me be clear, this is not some small niche trend. No way. This is a full-on gold rush. It's exploding because the need is real, and the market signals, they are loud and clear. And you want proof? Here it is. The market is expected to absolutely skyrocket to $4.3 billion by 2028. To put that in perspective, it was just over $1 billion back in 2022. I mean, that kind of explosive growth, it's not just a new product on the block. It tells you there's a fundamental shift happening in the very foundation of how we're building software. And of course, where there's that kind of growth, the venture capital follows. The smart money is pouring in. Just look at one of the leaders in this space, a company called Pinecone. They've already pulled in $138 million in funding. That's a huge vote of confidence. Investors are basically screaming that this isn't just some cool new feature, it's the future. But it's not just the big money guys, the top-down investment. What's really interesting is the bottom-up adoption. We're talking about the developers, the people actually building this stuff. And they are choosing solutions like Pinecone almost twice as much as the next best thing. This is that perfect storm, right? You've got the grassroots movement meeting that huge, big picture vision. Okay, so how on earth does this actually work? Let's geek out for a minute because we're about to dive into some really cool computer science. We've talked about the why, but now it's time for the how. And get ready, because it involves cracking a problem that for a long time seemed pretty much impossible to solve.
It all boils down to one core concept: vector embeddings. Seriously, this is where the magic happens. What we do is we take an AI model and use it to translate, anything, a paragraph of text, an image, even a piece of music. And it turns it into a long list of numbers. We're talking hundreds, sometimes thousands of numbers. That list, that vector, is a mathematical fingerprint. It captures the semantic essence of the original data.
And these aren't just random numbers. They actually capture relationships between concepts. The classic example is this. You take the vector for king, subtract the vector for man, and then add the vector for woman. And what do you get? Something incredibly close to the vector for queen. Think about that. We can literally do algebra with ideas. It's mind-blowing. Okay, but this amazing trick creates a massive problem. A huge one. Imagine trying to find the closest vector to your query when you're dealing with 1,000 dimensions. It's not like finding your neighbor on a map. This is what computer scientists call the curse of dimensionality. The space is just so unbelievably vast and mostly empty that checking every single point to find the closest one, it would take forever. It's just not practical. It's computationally impossible. So, what do you do when a perfect search is impossible? You get clever. You make a trade. The solution is to give up a tiny bit of perfection in exchange for a huge boost in speed.
Because let's be honest, for this kind of search, you don't need the one single mathematically perfect answer. You just need a really good one, and you need it fast.
And that brings us to Approximate Nearest Neighbor Search, or ANN for short. This is the secret sauce. These are the algorithms at the heart of every single vector database. Their entire job is to find close enough or very similar results, and to do it at lightning speed. And for searching by meaning, close enough is actually perfect.
Now, one of the most powerful ANN algorithms out there, you can think of it like a GPS for your data, a road network. The technical name is a mouthful, HSNW, but honestly, just remember the road network idea because that's exactly how it works.
So here's the play-by-play. When you do a search, you start on the top layer. Think of this as the interstate highway system. It lets you travel super fast across vast distances to get to the right general area of your data. Once you're in the right neighborhood, you drop down to a more detailed layer, like the local city streets. From there, you can navigate with more precision to find the exact address. It just keeps getting more and more specific until, bam, it finds the closest points. It's a brilliantly efficient way to search a space that would otherwise be impossible to navigate. Of course, HNSW isn't the only game in town. There are other algorithms, and they all come with different trade-offs. Just look at this table. On one extreme, you have an exhaustive search. Perfect accuracy, right? But it's so slow, it's basically useless. Then you have HNSW. Look at that, amazing speed and really high accuracy. But what's the catch? Well, it uses up more memory, and it takes longer to build that road network in the first place. The bottom line is, there's no magic bullet. It's always an engineering decision based on what you need.
And that choice, which algorithm, which trade-offs to make, is right at the center of a massive shift in the tech industry. So let's zoom back out to the big picture. This isn't just about a new tool. No, this technology has kicked off a whole new architectural battleground, a new database war.
Okay, if you remember one thing, let it be this. The database is no longer just a passive box where you dump data. Not anymore. A vector database is an active compute engine. Its main job isn't just storing stuff. It's constantly doing incredibly complex math. It's fundamentally blurring that old line between where your data lives and where the AI's brain works.
And as you can imagine, this has sparked some fierce competition. You've got players like Pinecone, Weaviate, Chroma, Qdrant. All of them are in a race to become the go-to platform. And for the people building AI systems today, picking the right one, it's suddenly one of the most critical decisions they have to make.
Which brings us to the big final question. As this new database war really heats up, it's about so much more than just who gets the most customers. The real prize, the real question is, who is going to build the ultimate memory for AI, the most powerful, the most efficient long-term memory for all of artificial intelligence? Whoever wins that race is going to define the next decade